This is a continuation of section 2.3. We've been talking about subspaces and span. Let me remind you about the notion of span. We're given a set of vectors, n vectors v1 through vn, and we say that the span of those vectors is the collection of all vectors that you can write as a1 v1 plus dot 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 a n vn as a1 through an as these run over R. So you take all the possible scalars that you can, multiply them times the vectors and add them up, and everything that you get is called the span. Here's a little bit of terminology, which I don't think I've defined, although I've probably used it before, which is a sum like this is called a linear combination. Of the vectors v1 through vn. So another way to say the span is it's all the possible linear combinations of those vectors. And remember, the way to think of the span of vectors is, I'll just draw a picture. You take this vector and you take this vector, and when you take their span, if you take any multiple of this vector and add it to any multiple of that vector, what do you get? Well, when you take any multiple of this vector, you get everything along this line, and you can get everything along this line, and then when you take sums, you get the whole plane. These two vectors, the span is equal to the plane. And one of the main things I want to illustrate is the following kind of example. What if I took this vector and this vector and this vector, these three vectors in R2, what's their span? Well, it's clear that their span is all of R2, just like the span of this was R2. As a matter of fact, I could have just managed with any two of these three vectors. I could have taken just the span of v1 and v2, or I could have taken the span of v2 and v3. Either of those would have done. The span of those two of those vectors is all of R2, and adding the third vector doesn't give you anything new. And the notion of linear dependence and independence makes this concept precise. What linear dependence has to do with is whether there are extra vectors or not. And this is what I mean by an extra vector. If you give me v1 and v2, then you don't need v3 to make this span. All right, let's look at that a little more closely. What am I talking about, extra vectors? So let's just draw a very simple example. Suppose I gave you v1 and v2, and I took v3 to be the sum. Then v3 is, so to speak, extra. You don't need it because v1 plus v2 is equal to v3. And another way to say that is that v1 plus v2 minus v3 is equal to the 0 vector. And this is a linear combination of the three vectors, and it's giving you the 0 vector. And the fact that V3 is extra is one way to think of that is that there's a linear combination of these three vectors which gives 0. It's a linear combination of V1, V2, V3, which is equal to the 0 vector. Well, there's an obvious linear combination, which is you take all the coefficients are 0, and this is one where the coefficients are all 1 or minus 1. So the point is it's a linear combination where not all of the AIs are equal to 0. By that I mean it's a linear combination A1 V1 plus A2 V2 plus A3 V3 is equal to 0. Well, it's obvious that you can find, if you take A1, A2, and A3 all to be 0, you can do this. But what's significant here is that you can find such a linear combination where they're not all 0. So that makes somewhat more precise the notion of having extra vectors. And just a little bit of terminology. This thing right here is sometimes referred to as linear dependence relation. Some expression, so a linear combination of these vectors which gives 0. Okay, so that leads to a very important definition, one of the most important definitions in the course. So I'll write it out. The definition, it's a property of a bunch of vectors. Suppose I give you n vectors. You say that these vectors v1 through vn are linearly dependent okay, that's linearly dependent if if you can find a bunch of numbers a1 through an, not all 0, not all equal to 0, such that a1 v1 plus up to a n v n is equal to the 0 vector. Okay, this is a very important definition. It's a little bit subtle. We're going to spend a little bit of time talking about it, what it means, and what the significance of it is. So, but let's just look at it again. It's a property of a collection of vectors. Here's a bunch of vectors. You're going to tell me that they're linearly dependent or not. And how do you tell? Well, the question is there some that you can find like this? You try and find numbers a1 through an, which makes the sum of the vectors equal to 0. Well, you could always take the a1 through an to be 0, so that's kind of boring. So to make it an interesting condition, something reasonable, you ask that you can find such a linear combination where not all of the coefficients are 0. And that makes them linearly independent, dependent. And if this doesn't hold, we say that these vectors are linearly independent. That's independent here is the emphasis. Independent, which is the opposite of dependent. So every set of vectors is either linearly dependent or linearly independent. Exclusive or, it's one of the two. All right, let's illustrate this with a couple of examples. So suppose you're in R2. Oops, let's do it in black. Suppose you're in R2, and you just gave me the two vectors like this, v1 and v2. Are these linearly independent or linearly dependent? Well, let's be really concrete. Suppose this is the vector 1, 0, and this is the vector 0, 1. So I want to know, can I find A1 and A2 such that A1 V1 plus A2 V2 is equal to 0, where these are not A1, A2, not both 0. Well, if you write this out, what is this? This is A1 times 1, 0 plus A2 times 0, 1. And of course, this is the 0 vector here is supposed to be equal to 0, 0. And that says that A1 comma A2 is equal to 0, 0. And that obviously, you can only do that if A1 is equal to 0 and A2 is equal to 0. And I asked up here, can I do it when they're not both 0? And the answer was no. And this is an example, these two vectors are linearly independent. And for two vectors, it's just saying that they're pointing in different directions. And let's look at the opposite case. Suppose I added a vector to this list and I took v1, the same v1 and v2, but then just for fun I threw in v3, which is the vector 1, 1, which is v1 plus v2. And I asked you, is this set linearly independent, v1, v2, and v3? Well, the question is, can you find a non-trivial linear combination of these three vectors, which is 0? Well, I just told you v3 is equal to v1 plus v2. v1 plus v2 is equal to v3. And that basically does it. That's a relationship between these vectors. Well, what do I mean? I'm asking for some linear combination of these vectors to be 0. So just bring the v3 to the other side and write v1 plus v2 minus v3 is equal to 0. So these three vectors, let's no, here they are, sorry. I should draw my line here. These three vectors are linearly dependent. And, one way to think of that is that this vector v3 here is sort of extra. All right, to illustrate a little bit more what this is about, let's look at a set of vectors, v1 through vn. And let's suppose that it's linearly dependent. So there's some linear combination of these vectors which is equal to 0, and not all of the AIs are equal to 0. Some of them could be, but they're not all allowed to be. And let's say for the sake of discussion that AN is non-zero. Then you can write this equation. You can bring the AN to the other side and divide both sides by that and get minus A1 over AN V1 plus ... down to minus AN n minus 1 over an Vn minus 1 is equal to Vn. So what I did is I brought this an Vn to the other side and made it minus an Vn. And then I divided both sides of this equation by by minus an, and to get this. Okay? And so to say that a bunch of vectors are linearly independent is exactly the same thing as saying that one of those vectors, this one here, is a linear combination of the others. And in particular, this says that the span of these n vectors, if you throw away the last vector, it doesn't affect the span. Oops. The span of V1 up to Vn minus 1, and you stop there. If you throw away the last vector, it doesn't affect the span. And the reason is that the span of these vectors is all of the linear combinations of these vectors, and anything involving this vector you can solve for, you can use this equation for Vn to eliminate it and get it as a sum of just the preceding guys. And that's what I'm saying here. The span is just of the first n minus 1. So you could ask yourself, suppose I have a bunch of vectors. Suppose I have a bunch of vectors v1 up to vn, and suppose they're linearly dependent. Well, what I just said is that that means that some vi is a linear combination of the others. And I took it to be the last one, but it didn't have to be. So maybe I should just say it's in general, all you know is that some vi is a linear combination of the others. So you take this set of vectors, throw away vi, and then do it again, and ask if you can get rid of any of them. And when you're done, you'll have a set of linearly independent vectors. If you have this v1 through vn, you can't throw any away. Can't throw any away. Well, that's exactly if you're in the situation where these vectors are linearly independent. A simple example of a little calculation. Suppose I gave you v1 as 1, 1, 1, and v2 was the vector 1, 2, 3, and v3 was the vector 2, 3, 4. Are these linearly independent or not? I'll let you think about that for a minute. Why don't you pause the video and decide, and then come back. It should probably only take you half a second. There we go. It's obvious that these are linearly dependent because v1 plus v2 is equal to v3. And one way to think about that is the following. take these three vectors and make them the columns of a matrix. And you'll see that the relationship between these v1 plus v2 minus v3 is equal to the 0 vector. Well, that's just putting 1, 1, minus 1 here. So the point is these coefficients here are 1, 1, and minus 1. And that's what's here. And if you just, if you multiply this matrix out, what do you get? You get 1 plus 1 minus 2, 1 plus 2 minus 3, 1 plus 3 minus 4 is the 0 vector. So the fact, let's never mind looking at the vectors over here. Let's think about things purely from the point of view of an equation. This equation right here, you can think of it as writing down this matrix, and you're finding x, y, z is equal to 0, 0, 0. And this is a very easy example, but gets the idea. And these are the coefficients. These guys here, 1, 1, minus 1. 1, 1, minus 1 are exactly the coefficients over here. And in terms of an equation, I'm saying if you wanted to find these, that would be the same thing as looking for this x, y, and z, which makes this hold. And of course, this is the original matrix here. 1, 1, 2, and so on. And in other words, I'm trying to solve a homogeneous equation. This matrix times this vector is equal to 0. And when does that have a solution? A non-trivial solution. This matrix equation has a non-trivial, which is to say not all zeros, solution well, when does it? In general, it has a non-trivial solution if and only if the determinant of the matrix is 0. And of course, that's what you saw up here. Where's my pen there? Up here, the fact that there's a linear combination of these rows, you can add, excuse me, that's easier to think in terms of the columns. You can add these two columns and get this one. And down in terms of matrices, it's saying that the determinant is equal to 0. So that makes a very good test. If you have n vectors, which are each n vectors, and the crucial point here is that these two n's are the same. This test doesn't work otherwise. This n and this n are the same. If you have the same number of vectors as you have the size, the dimension of the vector space, then the a convenient test for whether these are linearly independent, if and only if the determinant of the matrix that I described above is equal to 0. And so this A is the matrix that you make out of the columns. Make the vectors into columns.